Hi guys. Since I didn't get a chance to talk about this in lecture today, I thought I would go ahead and give you a quick overview of activity and systematic treatment of equilibria. So here we go. So one of the things to recognize about ionic strength is that ions have a different they have a different presentation in solution, okay? So they have water molecules around them, and so they have different behaviors. One of the things that we'll do in this chapter is we'll talk about that, and we'll come up with some ways to look at equilibria and try to figure out what is going on in the whole system. So this should just give you an idea of what the so when you look at the estimation of how this behavior changes, one of the ways in which it changes is the way in which the number of waters of hydration affected. And so, for instance, all the way up here you've got NH3 with 9, 10, 12 waters of hydration affecting it. So water binding to either the cation or the anion, right, is going to bind slightly differently, and it's going to bind through either the positive or the negative end. So ionic strength has an effect on solubility, okay? It's not just that you have to have a common ion, and this actually takes that into account. So we're going to talk a little bit about that. So if you consider something like this system, FeSCN, the FeSCN 2 plus on the right-hand side, the product is red, and on the left side, the Fe3 plus is pale yellow. And so if you look at what happens as you add KNO3, well, it's obvious, right, for this color plate on the right side here, that when you add KNO3, it becomes yellow. That means that you're creating more Fe3 plus. That means that you're shifting the equilibrium in this direction. And then this shows adding KNO3, so increasing the ionic strength by adding KNO3 reduces the forward reaction. So the question is why, right? It has to do with this ionic atmosphere, okay? So there are charged particles in solution already, and then there's an excess of oppositely charged particles creating some attraction. So the greater the strength of the solution, the higher the charge on each ionic atmosphere, which means that there's further attraction relative to just distilled water. And so the ions don't come together as much, right, because they have all that charge in solution. So look at it from the other direction, right, it promotes dissociation. So if you look at that FeSCN 2 plus that we looked at before, promotes that dissociation. You look at phenols, it promotes that dissociation. KHP promotes that dissociation. Sorry, that was potassium hydrogen tartrate before, not potassium hydrogen phthalate. But the effect on the potassium hydrogen tartrate can be seen as the concentration increases of these different solutions, right? So when there are no ions present, that's glucose, right? When you have NaCl, that is increasing ionic strength, as well as MgSO4, increasing ionic strength. This has the opposite effect, and you remember why, because you're adding more K, you're going to push it in that direction, right? So you have to be sure of what you're looking at. If it's a common ion, right, the common ion effect overtakes. So here's the equation, okay? This symbol indicates ionic strength. Ionic strength says that you take the concentration, and it's unfortunate that they show it as a C, but the concentration of each individual ion times its charge squared. Okay, so this is for number 1, number 2, number 3, and then this question mark just means goes on and on and on. It didn't translate in there very well. Okay, so that is the ionic strength equation, right? And so the summation of these these concentrations times their charges squared, so everything in solution. Quick calculation, right? Ionic strength of 0.1 molar NaNO3, 0.01 molar Na2SO4, and then this last one where you've got 0.020 KBr and 010 Na2SO4. Well, this didn't show up very well from the slide, but you get the picture, right? Because in this A, right, both of them are singly charged, and so it's just 0.1 times 1 squared, 0.1 times 1 squared, right? And then you take half of that and you get 0.1 back. Okay, so simple. But in this case, right, you have a 0.02 molar solution of Na, and then you've got a 0.01 molar solution of SO4, and the SO4 is 2 minus, so that becomes a 4, right, because that Z is now squared. And then the squaring of 1 continues 1, but note this, right, you have to look at the stoichiometry and be sure of the stoichiometry, because there are 2 moles of Na plus in every mole of Na2SO4. So you got to get the concentrations right, and then you got to square the charges. So this one got a little corrupted in translation, but I'll give you the explanation here. Basically, it is that as you have ions with greater than a charge of plus or minus 2, they don't fully dissociate. So if you look at something like this, you know, how much, when it's NaCl, how much of the Na plus basically is not dissociated, and it's only 0.6%. If you look at Cl minus, though, the Mg goes up because it's the 2 plus, it goes up to 8%. But then MgSO4, right, or Na2SO4, again, much higher in terms of the amount that is still bound as an ion pair in that formal solution of the metal and the ligand, as we're talking about here. So why is this important? Well, if you think about a lot of the things that we try to do, we try to look at things in cells often, and you know, if you've got ions not behaving the way you expect in single cell analysis, you're not going to get the right information back out. Okay, so again, we can take advantage of this by then looking at how much is actually occurring, right? So we can use these equations to find out really what's going on. So this leads to something called activity coefficients. When we talk about activity, that's what we're actually really talking about in an equilibrium situation, because the activity is what causes either more product or more reactant, right? It's not only the concentration. So how do you account for that? Well, you account for that by using this equation that says the activity, right, of C is equal to the concentration of C times the activity coefficient of C. So we're going to have to figure out what the activity coefficient is. So this activity coefficient, and this should be gamma, right? The activity coefficient, it measures the deviation from ideal behavior. And the numeric value is used to then adjust due to essentially ionic strength, right? When the activity, right, is equal to, or the activity coefficient is equal to 1, then behavior should be ideal. And there are conditions, in fact, many conditions that we use where that is the case. Okay, so this one got fairly messed up in translation, but here's what we're going to now, right? So when we've got an equilibrium expression like this, what we really are looking for is the activity, right? And then the activity coefficients, right, of C, the concentration of D, and the activity coefficient of D, and again, coefficient, concentration, and coefficient. And then those are being raised, both, right, are being raised to the appropriate power. Okay, so it's, again, it is the concentrations, right, times the coefficients that we're dealing with here. Okay, so if we want to look at a particular reaction, say this calcium sulfate, and what we want to know is really what's going on in this solution, we want to use the KSP of activities. So in order to get the KSPs of activities, you would use this equation, right? The concentration times the activity coefficient. At pretty low ionic strengths that approach 0, this activity coefficient approaches 0, right? So again, if the activity coefficient is 1, then the behavior would be ideal. I'm sorry, this activity coefficient approaches 1. So then it's reasonable to use only the equilibrium with concentrations, right? But if the ionic strength is increasing by adding another salt, then the concentrations effectively will increase, meaning that the activity coefficients must be used to decrease potentially, okay? Okay, so let's do an example, right? Here is lanthanum sulfate, and we're going to use activity coefficients to calculate the KSP. So the activity coefficients, we treat them the same way in terms of the exponents. So we'll square that, we'll cube that, right? Remember that the concentrations, lanthanum is going to remain whatever goes into solution. I'm sorry, it's going to be 2x, but the sulfate is going to be 3x, right? So we have to be careful in using the appropriate stoichiometry. Okay, so this one got severely corrupted, but in this, what we're looking at is the activity coefficient, right? So we're solving for it. So it's log of the activity coefficient. And that's equal to the negative 0.51 times the charge squared, right? And then the ionic strength, right, is put into here and down here, right? And then alpha, okay, is this last one that's in here, and that is essentially the ion size, okay? So this whole equation can be used to find the activity coefficient of a particular ion, right? So you have to find the activity coefficient of each ion that you're working with. So let's kind of sum this up a little bit. As the ionic strength increases from 0, right? So if you've got nothing in there but the what you're trying to dissolve, then it goes to 0.1. So as the ionic strength increases, the activity coefficient decreases, right? So as ionic strength goes up in this direction, this is going down, right? And the coefficient modifies the concentration. And so at these high ionic strengths, 0.1, you've got some of these metals, depending on the charges, right? And activity coefficient is all the way down below 0.1. That's a pretty significant change, right? Then as charge increases, it goes down faster. The smaller the ion size, the more important the activity effects actually become. Okay. So if you've got a table that you can work with, you can find the activity coefficients, but you can also use this Debye-Huckel. It's pretty decent. If you're in really concentrated solutions, then you have to use a different equation that we won't get into. So the thing that you do have to calculate first to use the table is the ionic strength, because it depends on the ionic strength. So if you look at this table 8.1 in the text, it's under the plus or minus 2, right? And it has a charge of a size of 600 picometers. And so it equals 0.675 at 0.010 molar, okay? And this is, again, the ionic strength, okay? I'm sorry, this is the activity coefficient, gamma. But this is what you would typically do, okay? So if you were looking for something like H+, right? And you would look up in the table that the size is 900 picometers. That's where this would then go in here, right? Again, ionic strength would go in here, right? And then this 305 is fixed. This minus 0.51 is fixed. Here's the charge, 1 squared, right? And again, here's the ionic strength, 0.025. So what you actually get out, right, is this negative 0.054, and they put the 98 on there. But that is the log, right? Remember that what you're dealing with is the log of gamma, and so in order to take the anti-log 10 to the minus 0.05498, and you get an activity coefficient of 0.88. So basically, activity coefficients of the non-ionic compounds, neutral molecules, it's not really worth working these out. They really don't have very much of an effect, and even though this slide's relatively corrupted, we're not going to worry at all about this. So these activity coefficients do have weird behaviors when the ionic strength is relatively high. And so again, that is where we would have to invoke a different equation and not the Debye-Huckel. So again, we're not going to worry too much about that, but recognize that there are limitations to using Debye-Huckel. So let's look at an example where we can use activity coefficients, and we can find the actual concentration of, in this case, calcium in a solution that has 0.050 molar NaF, and we'll try to figure out what's there. So in using this table, we find the ionic strength. An ionic strength of 0.05, we went through the calculation, and then we find that the gamma for Ca2 plus is 0.485, the gamma for F is going to be 0.81, plug those in using the appropriate exponents, and you get the concentration of calcium is equal to 4 times 10 to the minus 8th. So this kind of brings us a little bit of full circle. We're now going to talk a little bit about pH. So you can use, obviously, activity, right, to calculate a more accurate pH value. If the pH is equal to the negative log of the H plus, well, the pH is also equal to the negative log of the activity, more accurately. And then that becomes the negative log of the concentration of H plus times the activity coefficient. So when a pH meter is used, we're really taking the negative log of the activity, not the concentration. So if you looked at pure water, you'd come up with pretty quickly, you'd come up with 7. But if you use activity coefficients, not so fast. So the activity coefficients, obviously, you have to calculate those now, right? And so now we're going to find the activity coefficient for H plus and for OH minus. We're going to plug those in. We're going to use X and X because the concentrations should be similar, modified by that activity coefficient. So again, going straight up and saying, okay, these two are going to equal 1, right? You would come up with 1 times 10 to the minus 7th for X, and you'd come up with a pH of 7, right? So that would be in water with no ionic strength, right? But if we consider ionic strength, what happens? Now we've got some 0.1 molar KCl in there, and it's going to change. So again, we used the KW, right, where we got 1 times 10 minus 14, and then we can go to that table, and the table changes things a little bit because when you have an ionic strength of 0.1 molar, when you look up H plus and OH minus, H plus becomes 0.83, OH minus becomes 0.76. That obviously is going to change what the solution for X is. We plug that back in. Plug that back in to get activity out, and so now we've got the activity of the hydrogen ion, the activity of OH minus, and plug all of that back in. Well, actually, we don't plug all that back in. We already solved that. Plug the H plus into the negative log, right, because this is going to be the true activity, and it's 6.98. So you might not think of that as a very significant difference, but the concentration changes 26%. This is because of the pH scale, right? I mean, that's why we use negative log, because these concentrations are relatively small. So a change in 0.2 is a pretty significant change in the percentage. Makes a difference in a lot of systems. So how do you deal with this on a more system level? You use something called systematic treatment of equilibrium. I've referred to that several different times, and I just want to do a quick run through of how this is used. So in systematic treatment, your goal is to set up as many equations as you can. And so you deal with all the equilibria first. So, and I mean all of them, right? So if this is an aqueous solution, the one to not forget is H2O goes to H plus and OH minus. And then any of the other ones that are in there, right? If there are conditions that simplify, then do it. Then you can also potentially plug all this stuff into a spreadsheet if you're looking for these numerical solutions. So you write as many equations as you can. You write the chemical equilibrium, as many of those as you can find. You write a charge balance, and then you write something called a mass balance. All right, so let's go through and talk about what each of these looks like. So the charge balance is just how it sounds, and in the charge balance, you take the magnitude of the charge, so if it's a +1, it's just 1, if it's a +2, it's 2, and then you take the concentration of that cation, and you add up all the positively charged species in this manner, so that's why you're summing this, and then you add up all the negatively charged species in this manner, and that's why you sum that up. So this equation is essentially saying take everything that has charge to it and set the positive equal to the negative, and you got to consider molarity. So if you were to consider this solution, it's got 0.0250 moles of KH2PO4 and 0.0300 moles of KOH. So it's got what? H plus and K plus, right? And so you have to consider those concentrations. These are just going to be 1 times, right? So you add up those concentrations. Where do those come from? From the KH2PO4 going to H2PO4 minus, HPO42 minus, and PO43 minus. You got to consider all of those sources of H plus. And then the K, right? The K comes from here and from here. So you have to consider those sources. So that's just stoichiometry, right? But the other side, where you've got OH minus, right, you have to consider how much H2PO42 minus there is, and you got to multiply that by 2. And then the PO43 minus, you got to multiply that by 3. Okay, and that's going to bring you to a balanced charge in this solution, right? So this figure is saying, look, all that has to add up to a net of 0. Okay, so the next thing is mass balance, or what they call material balance. So this refers to the conservation of atoms in the solution. So where did they go, and how do they add all back up? So you have to look at all species containing a particular atom or group of atoms, right? And then that has to equal the amount that was initially delivered to the solution. So formal concentrations now, we go back to that, right? So whatever you put into a solution is got to equal, right? All the summation of the different pieces have to equal up to that original formal concentration. And we're not working with activity coefficients at this point. So let's look at something like acetic acid, right? Acetic acid, the weak acid, and so you know it doesn't completely dissociate. And so let's say you added a total amount of acetic acid into a solution. That would be the formal concentration. But it's in these forms, right? It's in the undissociated and the dissociated form. So you could write the mass balance to say the concentration of acetic acid is equal to these two concentrations. So looking at this concentrate or this mass balance, we could say that we know the concentration of K plus, and we know the concentration of all the phosphate species, but we don't know anything really about OH minus. So we could set up 2 mass balances here. One would be for the K plus, and one would be for the phosphate species. So here are the mass balances, okay? So the mass balance for this system, all of the K plus is in the same form. And so you simply take the formal from one and the formal from the other. That's it. But this is a little different down here with all the different forms of phosphate. They range from H3PO4 to H2PO4 minus to HPO42 minus to PO43 minus. And sorry, those superscripts and subscripts got messed up. But that is all equal to the formal from which it came, right? So it should make some sense to you because it was K3PO4 was this original 0.0250 molar, and now all of the phosphate that could possibly be in this solution has to equal 0.0250 molar. So one of the important things to consider here is when you have solutions that have stoichiometry involved, right? So this lanthanum iodate, okay, where it's La and then in parentheses the iodate 3, right, close parentheses, and there are 3 of those, right? So this looks something like this. If I can do it right up here, La, IO3, and 3, right? Because it's a -1, and the lanthanum is a +3. But the iodate is 3 times the total lanthanum, okay? And so when you consider the solution here, you know, down here, what are the total iodate forms? What are the total lanthanum forms? And so those have to be, the iodate total has to equal 3 times the lanthanum total. So you can also say something like Ag3PO4, what's that going to look like in solution? Well, if you don't know the concentration, you can just write something that says what is the what's the possibility here, right? So the Ag and the PO4s, so the Ag forms and the PO forms have a relationship, and so we can write a mass balance. So if the phosphate stayed in the form of just PO4 3-, you would write it this way, right? But it doesn't. And so you have to write it this way, where all forms of the phosphate are considered, right? And so now the Ag plus concentration is going to be equivalent to or equal 3 times all the phosphates. So why is this important, right? Well, here's an example of how this can have an impact. So this is calcium carbonate mass balance in rivers. So if the river lies along this line, right, then they have water saturated with CaCO3. But these rivers above, right, they have a high concentration of dissolved CO2. And that shifts the equilibrium and the mass balance ratio. And so that's not as conducive to certain types of aquatic life, right? So that difference is impacted again by the CO2 concentration, which is all impacted by those different factors that we've now talked about, right? Ionic strength, activity coefficient, and now mass balance. So just a quick couple of slides on applying systematic treatment. Again, you have to write all the pertinent reactions. You have to write charge balance. You have to write a mass balance. And then write all of the equilibrium constant expressions, okay? These 3 things, right, 2 through 4, right, you count the equations and you count the number of unknowns. If the number of equations equals the number of unknowns, then it is solvable. If they don't equal, then you've probably overlooked an equilibrium, or you've got to estimate something and say, okay, we're just going to have to make this estimation. Once you know all those, you can solve for all the unknowns. So you have to get used to this idea that you're going to have to figure out what chemical equilibria exist. The most common one that gets lost is water. And then identifying the reactions, so you may miss a couple, right? And then if you've got n equations and unknowns, it can be solved. It doesn't mean that you can solve this easily by hand. You may need a more complex approach, which is a spreadsheet. And then, do you really need to know all of them, or do you just need to know some of them, right? And so that can be a consideration in the end there. So here's a relatively simple one, right? All the species in an aqueous solution that has 0.01 molar NH3 in 1 liter, right? So now you know the concentration. So what are the considerations? Well, NH3 and H2O, right? So write a charge balance. Charge balance says that you've got NH4 plus and H plus, and then you've got only OH minus. Then write a mass balance. Well, you know that when you put that into solution, the ammonia is in the form of NH3 or NH4 plus, so that equals that original 0.01 molar. Write equilibrium expressions, right? And in this case, you write them with the activity coefficients, right? And now you write, or you figure out how many equations you've got. Well, you've got the charge balance, mass balance, the Kb, and the Kw, so you have 4. And you have NH3, NH4, H plus, and OH minus, and so again you have 4, and so this is solvable. So essentially what you're going to try to do is you're going to rearrange some equations, right? So particularly rearranging for OH minus to get it out of all of the equations that OH minus is in and have everything in the form of H plus. You can substitute the mass balance. You can substitute in NH4 plus and get everything in terms of NH3. You can then finally come back down to this, right? Because now you're substituting into the Kb, but you've solved for NH3 in the form of H plus, and you've solved for NH4 in the form of H plus. So ultimately what you get is something that looks like that, where it's only H plus and these constants. So again, you know, if you go into Excel, it becomes a much simpler problem, and you can use this thing called goal seek, and you read about that in the book, and it will tell you exactly how to set all this stuff up, and you can come out with all these concentrations, which is pretty cool. But you could also do this by hand. This thing is not all that difficult. You just start plugging things in and isolating the H plus. Once you isolate the H plus, you know, you get to a point where you can figure out what the pH is, and then you go back and plug it into each of the equations that you use to get there. All right, so that's all for Chapter 8, and we'll pick up with our next chapter on Wednesday.